Welcome. I want to get back to this total deformation of a Dirac matrix for a finite geometry. So here's the setup. It's very general, contains simplicial sets or simplicial complexes as special cases, but it's a computer science approach that we are just looking at the matrix D, which essentially defines everything about the geometry. So it gives us a cohomology, it gives us Euler characteristic, and we have a symmetry of McKean-Singer, which is extremely important, which immediately implies then this Euler-Poincare formula, that the combinatorial Euler characteristic is the same than the cohomological Euler characteristic, and it uses this heat operator, e to the minus TL. And this heat operator also plays a role for when we are looking at the deformation here. I looked at this in 2013. Of course, it's very close to all the Toda stories which were developed in the 70s and 80s, so 50 years ago, but it's a different story because we have here a geometric background. And the deformation really is exciting because the Dirac matrix, which a priori is just kind of has a zero diagonal part here. So we can always decompose a matrix in an upper triangular, a lower triangular, then strict upper triangular, strict lower triangular, and a diagonal part. And there will be a diagonal, there's a diagonal part. Everything is block diagonal, and so these blocks belong to the forms which the K forms. So these are the 0 forms, 1 forms, and so on. The result that you can take this Dirac matrix and deform it and get something, you know, more exciting with a diagonal part, which I call the dark matter part. And so that there's an electromagnetic part which belongs to the, you know, the Maxwell equations, for example, assume that the exterior derivative map K forms to K plus 1 form. The equation is dF is equal to 0, and which F is a 2 form, which is the electromagnetic field, and d star F is J is the current. So this is why I think about this part here, upper and lower, strict lower and upper triangular parts. I think about them as electromagnetic, and this is something we don't know. I call it dark matter because of obvious reasons, because we don't see it when we are looking at the electromagnetics. But it's also, this is equivalent actually, it's a Dirac matrix. Again, it's not isospectral, but it gives us the same kernel, so it gives us the same cohomology. And what happens is this actually goes to 0, and this kind of will dominate more and more. And in the limit, this only survives, and there is nothing here. And if you look at the Kohn formula, it means that this space expands if you measure with light, flashlight, right? If you measure with light, then that's what we do. Electromagnetic waves are used to measure distances. When you do that, then you get distance, and everything we measure is always based on measurements of distances, which is usually boiling down to solutions of wave equations, partial differential equations, which involve the Laplacian. So that's the reason why I think about this part as the electromagnetic part and this part as something we don't see, but it's there. And but here, this is extremely exciting. I'm really very, very excited about it because I thought there is no kind of direct correspondence between the QR decomposition. I saw 2 weeks ago that the QR decomposition actually produces something like this, but it was not obvious to me why, if you make that and you do that, that this is again a Dirac matrix. And actually, I gave you a wrong proof. This is a proof I kind of thought about while proctoring an exam in summer school. It was a wrong proof, and also the last week I did not give you the argument why this is actually true. This is the reason why this works. So we know, that's what I have shown in 10 years ago, that this is actually produces a deformation of the Dirac matrix. But it's not clear if you take this and then compute this conjugation, right? If you kind of deform this, kind of look at it as an observable in the Heisenberg picture, so deformation, nonlinear deformation, that you get here, again, a block diagonal thing. It's not obvious because the Q itself is not in the algebra of D, so the Q square is no more block diagonal. So the Q is an orthogonal matrix, but it has the same form, tridiagonal form, but it's not in that algebra. It's not of the same form, and also the R. How do you actually prove this? And so here is the proof. Let me give you the proof. So Q dot is the derivative with respect to t, and I write this like that. So Q prime dot is equal to, so there is a differential equation like that. And this is t. E dot is notation G I dot G. Might get the sign wrong, but let's just see, minus G of D0. So just to wrap up the proof, I had a sign difficulty, and that's it for today.